Next lesson. Materials. Ideal gas law.
We did it.
No, we didn't.
No density.
Did we do 2 lessons?
No, we didn't do ideal gas law.
Yeah.
We talked about it.
We just talked about ideal gas. We didn't talk about ideal gas law. Yeah. All right.
There's no way.
No way. What?
Escape from.
No.
Why?
You want that lesson in August 9, or
Yep.
we should do it in the August 9?
Yeah, travel back in time and do it in August 9th, 2016.
Know your plan when you write the.
No, that's just the last time I changed the file. Made a change to it. Like update it. Yeah. Can I just put this into this adapter too? Let's do that. Okay. Ideal gas laws. You write it down? So. Couple of laws to do, couple of definitions, no big deal. So, this might be a law you would have heard before. Boyle's law. Maybe. I don't know. Have you heard of Boyle before in physics or in chemistry? Boyle's law. Think back. Nope. Boyle's law for an ideal gas states that P is inversely proportional to volume. This means as the pressure increases, the volume decreases, or vice versa, provided that the mass and temperature is constant. So as a formula, Boyle's law can be stated as P is proportional to 1 over V, or another way to state it is that P times V is a constant. Simply put, Boyle noted that if the volume is halved, then the pressure is doubled, or vice versa. What might be the other relationships between P, V, T of a gas? Coming up after the break. So if you can write these down, we'll have a look at some other relationships between the variables. Have you heard, does this look familiar? Not for you? Not for you? Are you sure, you guys?
Is it PV equal enough?
It's not that.
It's the only
Okay. Boyle is was a Irish physicist and chemist. And this law is named after him. And he's actually buried near the school as well. He's buried at a church, St. Patrick's Cathedral, I think, which is not that way. If you come out of school and turn right, and then at the traffic lights turn left, and continue for a little bit, there's a cathedral that you pass. This is the cathedral he's buried at. Anyways, I don't know. I thought you might have heard his name before, Boyle, but I guess not.
We should.
Or maybe in Arabic, Boyle.
Yeah, I heard his name, but
Did you?
yeah, but I don't remember what is the formula.
Okay. He'll be touched, so. Right.
We should write the formula only, or?
It's enough to note these two. What?
The formula.
Yeah, these
We come
two.
for in the exam like step 5 law.
Yeah, but you can give it like this as long as you explain what the P and the V is.
Yes. Yeah.
You're making my life hard.
It's the weekend.
I know it's not. It's nearly the weekend.
Yeah, I want you to be happy with it.
I won't be teaching you, so I will be happy. Trust me. Okay. Right. Next now. So it will not surprise you to know that temperature and pressure are also related. So if you were to have a guess, what do you think the relationship might be? Increase in temperature would cause what to happen to pressure? Yeah. So from day-to-day experiences, we know that if temperature increases, then pressure increases. Until kaboom. So the pressure will increase until an explosion. Now, another thing that was noticed by Kelvin, when Kelvin was looking at different graphs, he was at different gases. What Kelvin was doing was he would take a gas, let's call it A, and he would heat the gas. What exactly was he doing? Well, I guess it wasn't. No, it was like this actually. Yeah, sorry. He would heat the gas up, and he would note the temperature and then the pressure of the gas in the container. So he saw, okay, I heat the temperature up and the pressure goes up. So he puts the points on the graph. He did it for a different gas, and he puts the points on the graph, and a different one, and so on. And he draws a straight line. And what he noticed was that for all his gases, they all meet back at minus 273 Celsius. That he could never find a gas that could be less than this number. Because once you go past this, you can't, because the pressure is zero here. You can't go under the axis. So he noticed that this was representing some kind of limit that all the gases could reach but not pass. So he reasoned that this must be the coldest the gases could be. So this gives us the idea of absolute zero, meaning the coldest anything can be, minus 273.15. So it didn't actually matter if it was a gas or whatever it was. It turns out everything is like this. So this gave him the idea of setting up a new scale. He called absolute zero as the lowest possible temperature. And I don't think he called the unit after himself, but he came up with a new unit, which we call the Kelvin, which is nearly the same as the Celsius, but with one big difference, as you probably know from chemistry. You increase it by 273.15 units. So in other words, if you want the temperature in Kelvin, it's the temperature in Celsius plus 273. The advantage of using this is that the temperature is always a positive number, and actually what would be the smallest temperature in Kelvin? It would be zero then. Because what's the smallest temperature in Celsius? Minus 273. So minus 273 plus 273 is zero then. So the Kelvin is defined as a scale of temperature with absolute zero, the coldest anything can be, as 0 Kelvin, and the triple point of water as exactly 273.16. Now, the definition might seem a bit weird because I've never actually told you what a triple point was. And it's not really something that's on the course. And the only time it appears on the course is for this definition. So I don't want to get into the technicalities of what the triple point is. So I'll just cheat and say the triple point is like the freezing point of water, which is 0 Celsius. So you might say, well, hang on a second, Stephen. That doesn't quite seem right, because 0 Celsius, if I put 0 here for Celsius, what's the temperature in Kelvin? 0.15, and I wrote here 0.16.
Oh.
This is what I mean. The triple point isn't quite as simple as I'm making it sound. I'm just saying the triple point is the freezing point of water, but it's actually more to it than that. And something you don't need to know about. So this is the formal definition of the Kelvin. It has been asked in the exam. It is something that you need to know. These two, I've seen them in the exam. You see, the material section of the course is not that big. It's a bit like the waves. And you might notice from the waves in the exam that they like to ask you definition questions. And they do this when they don't have many questions that they can ask you. So this is something you would need to know for the exam. So you should write these down carefully. And before you ask me, Sharif, it must be exactly like this. Every word. No cutting anything out. Yes. Okie dokie? Not okie dokie. It hasn't stopped raining since, like, I don't know, what time did it start? 12 o'clock today?
Thank you.
Since yesterday. Stopped for a little bit this morning. Okie dokie? Not okie dokie. Okie dokie should be. Okie dokie. Right. How do we count in physics? I know it seems like a silly question. You might think, well, like in everything else, 1, 2, 3. But in fact, when we count, we do not use a unit or a scale. I'll give you an example. Imagine we had some water. We do not say we have 10 to the 23 molecules of H2O. I mean, you can say that, but that's not usually how we count molecules. So what do we use? We need a unit to count. So for example, I'll give you an example by what I mean. Bakers count in 13s. So for example, if you ask a baker for something called a dozen, you know this word dozen? D-O-Z-E-N? Write it down, Mr. if you can look it up. D-O-Z-E-N. So to a baker you would count in dozens. You'd say 1 dozen, 2 dozen, 3 dozen, which would mean 13, 26, 39. You know this? No? Yeah. So 10 baker's dozens of cakes would be 130 cakes. Yeah. If you talk to a farmer also counts in dozens, but a farmer's dozen is 12. So he would say 1 dozen is 12, 2 dozen is 24, and so on. In physics, we don't count in units of 13 because that's too small of a unit, because we're usually counting big things, you know, number of atoms, number of stars, they're all big values. So we use something you would have seen in chemistry, called Avogadro's constant. So we count in units of these constants here. So a mole of something, and it can be anything, molecules, cups of coffee, stars, is 1 Avogadro's constant of that something. And 1 Avogadro's constant is defined as this number, 6.02 times 10 to the 23. This is the scale that we usually count in physics, because we need to count many things. Why this number? You probably know the answer already from chemistry. It's useful for other things which we'll see later. So anyways, if I have 1 mole of H2O, how much H2O do I have? Or a mole of cup of coffee, or a mole of stars, then I have that many molecules of H2O, that many molecules of that many cups of coffee, and that many stars. Okay, just the definition is enough. And yes, Musharif, if you want to write down 1 mole equals 1 Avogadro's constant equals 6.02 times 10 to the 23, that's fine. Because I know you know this from chemistry, right? You got that? Yeah. Imagine I have 1 mole of cups of coffee. That's a lot of coffee. Might drink that many in a day. Who knows? What would the mass be? Well, it'd be a pretty big number, wouldn't it? If I had that much coffee, right? I mean, we have, what's the mass of this? 100 grams? If I had a mole of this, that's a lot of coffee to have. So, let's calculate it. Yeah, we'll estimate it. So what would we say the mass of this is? 100 grams? Would that seem right? 200 grams? What do you think? Let's say 150. We'll go in the middle. So 0.15 times Avogadro's number. Tell me what you get, please, if you have the calculators there. Now, I think Avogadro's on the calculator already. Oh, rats, where's my calculator? Where's my... It's not on the table, is it? No, I don't have it right now.
You should use your calculator.
No, but I need the lid to see the constant numbers on it. I don't know which number it is. Do you have the lid? I could keep trying the constants until I get it. Oh, please. Right, I'll just type it in. 0.15 times 6.02 times 10 power 23. 9 times 10 to the 22 kilograms of coffee. A lot. Yeah? This is called the molar mass of coffee. That is, the molar mass of material is the mass 1 mole of it would have. Please note, it's common to give this mass in grams. However, I think that's just because that's what's done in chemistry. In physics, we would immediately change it into kilograms. But it's common practice to give molar mass in grams. You probably have noticed that in chemistry anyways. Okay, this is all easy stuff for you right now, isn't it? So for example, the molar mass of H2O is, so how much would 1 mole of it be? Much less than for coffee, because H2O is much smaller than coffee. It's only 18 grams per mole. So 1 mole of H2O, you've got 18 grams of H2O. Some important notation. We normally let big N represent the number of molecules and small n is the number of moles. At least that's what I use and we use in physics. So here big N is for a big number like number of molecules of H2O, whereas small n is a small number, the number of moles of H2O. So we actually have this formula that can convert between number of and number of moles of. And this I'm sure you've done many times in chemistry. No, but you might have written it differently just. Look, if I said to you the number of molecules equals the number of moles times Avogadro's constant.
Oh, yeah.
Yes, I knew. Yeah. Trust me. So, here's a little hint to remember it. Big N is bigger than small n, so you shouldn't. Your big N should be a big number, and your small n should be a small number. Okay, I don't know if you need to write anything down here, or is it all okay? You're familiar with molar mass, of course. Yep. Right. Let's see how a little bit of chemistry revision. Let's see how good you are. You could have this in chemistry, right? I give you 1 liter of water. You use liters in chemistry, don't you?
Yeah.
And I give you the molar mass of H2O. There it is there. And here are some questions about how many moles there are, how many molecules, how many oxygen atoms, how many hydrogen atoms. Okay? I think you should be having no trouble with this. I'll give you 1, 2, 3 minutes. Maybe 4 minutes if you're feeling a bit sleepy. If you want a little hint, Musharif, a little hint, I shall remind you that 1 liter of water has a mass of 1 kilogram.
1 liter of water, yeah. Yeah, I know.
Okay, right, fine. I'm just going to sip my coffee and then give you the answer in a minute. Making progress, Iyad?
Yeah.
Yep.
My calculator is right now.
Your calculator as well?
Right now.
Sure, isn't he flying home today or something?
Yeah, he was late.
Yeah. Make sure you get the calculator back off him or you'll never see it again. You'll get lost in the airport. That calculator that I use, I uploaded it to Noodle.
Oh.
Yeah, so you could download it. I can't remember. I probably put it on the. Oh goodness, what I don't know if I put it on the maths page or the ICT page or the physics page. I put it on one of my pages, I think. I'd say I put it under books and resources if I did put it on my page. Finished missionary?
No, it's not. I don't know.
Great. Okie dokie.
Yeah.
I'm going to do it now anyways, yeah. So, we have 1 kilogram of water. That means we have 1,000 grams of water. How many grams in a mole? 18.01528. So just get out the old calculator and hit in 1,000 divided by 18.01528, and we have 55.5 moles. Next, how many molecules of H2O do we have? So the number of molecules will be Avogadro's number times this answer. So I'll just take my answer here and multiply it by my buddy Avogadro, 6.02 times 10 to the power of 23. And that's 3.34 times 10 to the 25. Molecules. Of H2O. How many oxygen atoms do I have? Is it? What do you think? Is it the same as this?
No,
Interesting. Interesting. Over 3.
yeah.
Not over 2? Not over 1? It's this. It's the same.
Really?
Yeah, really. Because, think about it. Here's H2O. Hydrogen, hydrogen, oxygen. Let's say I told you I had 100 of these. How many oxygens would you have? Of course.
How many?
Could you say to him? I haven't got the energy to repeat myself.
We have 100 of these. Then how many hydrogens?
Oxygens.
Oxygen.
Yeah.
100, because it's just 100.
Yeah? So now this should inspire you for the next part, which of course is how many hydrogen atoms do I have? Oh, so close, but yet so far. Times 2. Because think about it, if I said I had 100 of these, how many hydrogens would I have?
Yeah.
200. Because each one gives me 2. Yeah. Can you see that? Yeah. So, 6.68 times 10 to the 25. That's how many oxygens, and that's how many hydrogens.
It should be 6.68 to 10 to 50.
Nope.
Why?
Oh, you know why. The 2 just multiplies the number in the front. It doesn't change the power.
Okay.
You are thinking of squaring.
No.
Ah, yeah. Trust me.
But that's zero.
But it's in the power.
Think about it, double that is definitely not. Well, this is like.
Yeah.
This is 25 billion, whatever you want to call it.
Yeah.
So the double of that is definitely not 50. Yeah.
Yeah. Okay, continue. So, next. Let's go back to Boyle's law for a moment. It won't surprise you to learn that there are other relationships. This is Boyle's one. Pressure is inverse to volume. Pressure is proportional to temperature. We discussed that earlier. Increase the temperature, increase the pressure. Do you want to have a guess at some other ones? Like, for example, I don't know. Well, no, we won't guess them. They'd be a bit too tricky. Volume is proportional to the number of molecules, which makes sense. If you double the number of H2O molecules in your liquid, then you've doubled the volume. You have twice as much. And pressure is also proportional to N. You double the If you double the number of H2O molecules but don't let the volume increase, then you've just crammed more inside, so you've doubled the pressure instead. And volume is proportional to temperature, so if you increase the temperature, it will expand in volume. So anyways, all these relationships, they're all coming from one formula. And by looking at the relationships and thinking about it carefully, you can end up with the result known as the ideal gas law. PV equals N or T. If we use moles, that or is a constant, and PV equals NKT if we use molecules where K is a constant. So you have a different constant depending on whether you are using moles or molecules. Now, which one do you use in chemistry? Probably always moles. Yep. Rock and roll? Continue? Yeah? Okay. Let's check the dimensions of these constants. So, if I have PV equals N or T, then the N is PB over RT. So, oh sorry, I screwed that up. I meant to say the OR is PV over NT. Now, you might remember recently I asked you to check what the units of PV, what the units are. Do you remember what the units of PV is? Correct, which is also called, it is not joule. Remember, last time you said trouble remembering it. So that's joule, and the unit of N, what's N measuring? Moles, and T, temperature, Kelvin. So the OR is in joules per mole per Kelvin. Likewise, what would the K be in? That would be in joules per molecule. Molecule, I guess it's close enough. Per Kelvin. Or per Celsius. It's the same thing. So these are the units. And I haven't given you the values of these constants yet. But there is something kind of weird here that always annoys me a little bit. Dividing, we see they're the same formulas with just a different constant if we're using different units. So what I mean here is, if you look for a moment here, we have PV equals N. I realised that after I wrote it. N or T. And you also know that N equals N times Avogadro's. Yeah? So you can say N equals N over Avogadro. If you just rearrange that. Yeah? So if I if I change this N into N over NA, that's big N and big NA, times RT, I can get PV equals R over NA times NT. Now, it turns out that this has the same value as that constant K. So, to me, it seems like you have two formulas which are not necessary. You only need one of the formulas, because the other formula you can arrive at from the other one. You know, it's a bit like me saying, oh, V equals U plus AT, or we have this other formula that says U equals V minus AT. You know, that's not two different formulas. You've just rewritten one of them into a different form. And that's really what's happening here. If you convert the N, small n, into big N, it changes the constant, and you'll get the other formula. So, K is called the Boltzmann's constant. And they're really the same thing with just different units. So why do I need constants? After all, if PV equals N or T and PV equals N, NA or T, since N equals NNA, I don't know. I was just rambling here about why I don't feel like there needs to be two formulas. You need to ask a chemist. But, anyways, I was rambling when I wrote that. You can just accept that you don't need two formulas, but we have two formulas anyways. And the only difference between the formulas is the constants. The first constant you know from chemistry already. When you're using moles, the OR has value of 8.31. This you know. When you're using molecules, the K has this value, 1.38 times 10 to the minus 23. Both of these are on your calculator, but I've lost my calculator, so I can't tell you what number constant it is. And anyways, you don't have that calculator, so you need to write these down. Finally, note that, oh yeah, this is red, critical. Critical. We always use Kelvin in these formulas. So, although you can write Celsius here, it's better in your brain to think of this as only allowed for Kelvin. If necessary, yes. Yeah? Nope. Yes? Say yes? Okay. So from now on, we will just use Kelvin to be safe. Right, here's some molar mass values that you might find necessary for some calculations. So the first one is liquid water. Before you write them down, let me just explain. Liquid water is 18 grams a mole. The heck, why does it say mole cubed? That should be -1, of course, not cubed. I have to fix that. Anyways, 18 grams for 2 hydrogen and 1 oxygen of water. Why did I say liquid? Because it's, oh, never mind. Carbon dioxide, CO2. CO2, 1 carbon and 2 oxygen. That's 44 grams a mole. Hydrogen is 2 grams a mole, and it's 2 hydrogen is the structure. Helium gas is 4 grams a mole, and it's 1 helium atom. Did you do the name in chemistry for when you have an atom that exists in pairs? So, like for example, hydrogen exists as H2. I think like oxygen as well, O2. A helium can exist by itself as 1 helium atom. Do you know the name for when atoms have to occur in pairs?
Yeah.
Very good. Diatomic, yeah. Oxygen is 2 oxygens. It's about 32 grams a mole. And finally, the other important one is, now of course you don't need to know these for the exam, and we give it to you in the question, but you might need to know them for the worksheet. Nitrogen gas is 23 grams a mole, and nitrogen is N2. Yep. Okay, I think you should write these down, and then you can try the next question, which is another chemistry question. Yeah. Alright, take a picture too. Do you just want to take a picture of it? Because you don't need to know them for the exam, you just need to know them to do the questions. I'm not expecting you to remember these, not at all. Is that not your phone?
Yeah.
I can continue? Trying to get a good angle.
No, but
Right.
yeah.
What? Are you teaching him something new on his phone?
I want to learn how to do it. That's a good sign, actually.
Yeah.
What? No.
Continue.
Yeah, no, sorry.
Right. So just this one more question to try. Again, it's something kind of like what you might do in chemistry. So before you started, you have a cylinder, and at this point you all remember what a cylinder is. Moucherie, you remember cylinder?
Yeah.
What is it?
Not this yet.
It's which shape?
This yet.
Good enough, good enough. The radius is 30 centimeters, the height is 1 meter, and it's filled with helium. The tank is in a warm room of temperature 26.85 Celsius, and therefore the tank is at this temperature too. The tank has a pressure of 3 atmospheres. Part 1. How many moles of helium are in the tank? Okay, so if you can try this, how about we just do it as ABC? So just do part A now. This shouldn't take long, it's just a chemistry type of question.
This is the homework?
No, this is an example to practice in class. What's wrong? I'll give you a little hint. You will have to use PV equals N or T. So you know the P, you know the V, you want the N, you know the OR, and you know the T. So you can get me the N.
And I found all of them, but not the one that works.
But why do you have pens in your bag that don't work?
Yeah, I should.
You should do something about that.
Yeah, but I'm too late.
That's okay. When's the last time we had 4 students? 2 weeks ago, maybe? You got your calculator working, the download? I can look at it later. Did you try to open it and it said something was missing? There's inside the folder, there's another file that you can run if you're missing what it needs to install. It's called like support folder.
Yeah.
And inside it, is there another exe called something like Visual Basic or VB or... Is there another executable file?
Yes.
Yeah. This installs what you might be missing. Okay, did you get an answer, Mashri, for the first part?
So I have to use the K.
PV equals N or T.
I don't have to use K. Kelvin.
Yes, you do. Remember, I said you must use Kelvin. Yes, I said you must use Kelvin. I didn't say use Kelvin if you want. I said you must use Kelvin. Must.
I have to use the second law that says PV equals N capital K E O.
No. What do I want? What do I want? Moles. Is that big or small n?
More. And the second one that I have to use that.
Yep.
Or
Or you can use Avogadro's constant to convert it. Yes, it is. Okay, let's have a look at this now. Oh, come on. PV equals N or T. So N is PV over or T. What did I say the pressure was?
Yes.
So that's 3 times 101.35 times 1,000. And the volume is pi r squared H. And the R is 8.31. And the temperature is 300, I believe, when you add on, isn't it? Yeah, 300 when you convert it.
Yeah.
So, I don't know, did you type this in or do you need me to type it in?
I did it.
Okay. Let me type it in then. Alright, no, I got it.
I typed it later. Does that make sense?
No, it doesn't. Let's see if we get the same one then.
Yeah.
It is.
in mine, I calculate all the top and then I divide all.
Exactly, and I told you at the start of the year, this is the calculator I recommend. Right, what did you get, Iad? No, don't be shy. We're all friends here. What did you get? Go on, don't be shy.
273,437.08.
Whew, it's a big number. Not 34 then. Okay, so you must have hit something wrong then. 34.48. And the next part is to get the number of molecules. So what do we multiply this by? Avogadro, yeah, 6.02 times 10 to the power of 23, and we'll get 2.07 times 10 to the 25. And finally, for this part, is how many atoms of helium are there? Now, yeah, is helium diatomic or not? No, so it's the same number then. Yeah? Is that okay, guys? Yeah. So now next part. Oh, sorry, that was 1, 2, 3, not A, B, C. So now is part B. Okay, part B1. Some gas is allowed to escape from the tank. The new pressure is 2 atmospheres. How many moles of helium are in the tank now? Now when you think about it, that's the exact same question except what has changed? 3 to 2. Yeah? So how many moles of helium are in the tank now? What did I get previously? 33.48, wasn't it? So if you retype this in your calculator, but just change this number from a 3 to 2, you get the right answer. Okay, so let me just do that for you.
You can't go to the.
Oh yeah, I can do it that way too. It should be 23 about. Yeah. See, this calculator rocks. Go back and change that to 2, and you get 23 about. We'll say 23. 23 moles then. So, how many escaped? How many moles escaped? Well, if you started off with 34.48 and there's only 23 left, then 11-ish, yes, 23 left, then you're left with 11.48 moles is left. Part C. This is an interesting one. What was the volume of the escaped helium?
So you
So yeah, let's look at the formula. PV equals N or T. So we know how many moles escaped, correct? We know the R, correct? We know the T because I said very clearly that it's the temperature of the room and the tank. So we know the T.
Yeah.
The volume is what we want. Do we know the pressure? What's the pressure of the helium gas that escaped into the room? No. No. Wasn't 2 or 2 atmospheres. Yeah. We want to know the volume of the helium that escaped from the tank into the room. We know the temperature of the room. We know the number of moles of helium that escaped. We want the volume. Do we know the pressure of the helium gas that has escaped into the room?
1.
Yeah, why?
So 3 on, the room that you know.
No.
Why?
You had the right answer, but for the wrong reason. What is the pressure of the air in this room? 1 atmosphere, the pressure. Remember, I said the pressure at sea level is usually 1 atmosphere. So in this room right now, this air is at 1 atmosphere. Anything that escapes into the air, carbon dioxide, oxygen from plants, helium from a tank, it'll all be at pressure of 1 atmosphere in the room at sea level. This is a fact. So in fact, this we do know. It's 1 atmosphere. Okay, now you got the right answer but for the wrong reason, okay? So we want V equals N or T over P. So that's equal to 11.48 times 8.31 times 300 over 1 times 101.35 times 1,000. .28. Easy peasy? Yeah, so easy. Why are you doing this baby stuff with us, Stephen? If the tank was left open until no more helium escaped, how many moles of helium will be left? So you might think, oh, so if I leave the helium tank open, the helium will keep escaping. It doesn't really, because if it keeps escaping, then what you would have left is a vacuum, and you know that doesn't happen. What's going to happen is the helium will keep escaping until what? Well, until the pressure on the inside of the tank equals the pressure on the outside. The reason the helium is escaping is because the pressure here is higher than outside here. So it's originally at 3 atmospheres and then 2 atmospheres, so now it's going to continue until it'll be at 1 atmosphere of pressure. Then there's no reason for the helium to escape because it's at the same pressure as the air on the outside. So the helium will escape because what will happen is the helium and the air will just mix around. It'll kind of be like it'll be a bit like this. If I put this coffee cup into the ocean, it will be at the same pressure as the water. So you might say, oh, the coffee won't leave. But what will happen is because the air is actually moving around, the coffee will just over time mix in with the water. So if we want to know, we just have to use our formula again. PV equals N over T. N equals PV over RT. This time the P is 1 atmosphere. The volume is pi r squared h. 8.1. Oh, thank you. So I actually forget about that. 8.31 times 300 then. This number should, of course, be smaller than the previous number of how much was left. Anyways, let's calculate it. Actually, is there any? No, I won't go back. I'll retype it. 101.35 times 10 cubed times pi times 0.3 squared over 8.31 times 300. 11.5 moles will be left in the tank. No, yes. 11.5. Okay, so you might need to write that one down too. That is the part C. Be strong, Musharif. We are not finished now. I'm going to give you time to work on the questions.
And we did them here.
What?
And we did them.
It depends on how many questions I gave you. Be strong. Continue. Okay. Let's see how many questions I gave you. What do you feel like? A lot? A little? You think I gave you a lot? I don't actually remember. Let's see. Not so. Only 6.
You didn't grade 7 before, so.
How do you remember this?
Yeah.
You remember that 6 is the maximum? Is this the new maximum? There's been a 6 before?
Yeah.
Right. So now you see, now that you told me there's not been a 7.
There will be a 7.
Okay. Guys, I think this stuff is okay because you did it in chemistry as well, you know, so you shouldn't find it too hard. I know that probably, would it be fair to say it's more difficult than what you're doing in chemistry, or not?
I think in chemistry is more straightforward.
Yeah.
I think
a bit of
it's
extra
the
stuff.
easy.
It's easy, it's just more difficult.
Yeah. Okay, try these for a few minutes, Musharif, and then your weekend will begin. If you want, you can listen to some music as you work. Okay? I need to close this as well.
Why? Close the record, but yeah.
No, because I want to send an email to the bank. I don't want you to see what I'm saying to the bank. It's private.
Please.
Please call me. Please. Do you want to take a picture on your phone now that you learned how to focus the image? Yeah. Right, once you take the picture, I'll put the light on. But you might as well just send you the image from Google, the PDF.
Right.
Can I put the light on? Yeah.